In this video, our team has partnered with the manufacturer, New England Airfoil Products, to bring you a realistic and applicable user story in support of the Department of Defense and its digital transformation efforts. You'll hear from their North American president, who will share the ROI of this investment, along with their engineering manager, who is responsible for the integration and adoption of new technologies.
To me, that's the best tank in the world. And it's been around for ages because of that. People don't think of airfoils as being anything fancy, but it's a very highly engineered product, complex to make, and newer engines, more complexity. We make the compressor blades on 9 stages of the compressor. We serve the aerospace industry and the military on some of the advanced engines. Army side, we serve the Abrams tank, and now we're on a ramp-up pace with them, as there's obviously geopolitical need for more, I would say, engines and blades from the Army. We have 9 dedicated cells doing this product line. We reserve that capacity due to the need of the Army. Sometimes it comes in waves, so we need the ability to flex when we can. We have been asked, how can we raise our production? Here at NEEP, what we have been looking at is not just how can we add more people, how can we add more machines, but we also have been looking at the methods of manufacturing. So how can we get more out of the current machines? How can we get better cycle times, faster production, faster inspection steps? I think one of the things we've looked at, and working with CCAT, who has been a great partner to us, is looking at software. With Third Wave and the software that they brought to the table, we were maybe a little bit skeptical of that because we have tried everything already. So here's something new to throw at to the, how do we do this? And I think CCAT played a key role of bridging that gap and making us more comfortable to see the benefits and work through this process with us. Third Wave has brought up to 50% savings in time, processing time on the machine. We were able to make almost 2 parts for every one before. We experienced better tool life. It also is less strenuous on the machines itself because the software is optimizing the way we're working. The cost of making the parts then starts to go down. Our scrap rates have went down. The data collection that the engineers are able to collect from it and see in real time is something we haven't had before. So the benefits of it are in so many different areas, has made the process really even exceeded our expectations, I would say, of what we originally thought we were gonna get with this software. Brian, our engineering manager, who's been on the project since it started, will be able to take you through some of the software optimization, how it was implemented, so you can understand what it really did for us on the floor.
Hi everybody, I'm Brian Jacobs, the engineering manager here at New England Airfoil Products. Welcome to our shop floor. We're currently in the middle of our Go Mill Lichty Go Mill 350 cell. Here we do some complex airfoil blades and vanes, and I'm going to use this area to show you some of the optimization parameters that we've been using in this cell to really gain a technical leverage for our company here at NEEP. First thing we're going to do is we're going to open up our CAM solution right here. So right here I have a demo part that we have. So this is a part that we use to simulate multiple types of cutting analysis. So what I'm going to do is I'm going to kind of walk you through a small demo of how we would go through an optimization for any of our products here. So right now what you see on screen is that demo part, and I'm already in my CAM solution side here. So what I'm going to do is I'm going to navigate over to the manufacturing part of the NX solution. I'm going to highlight my 2 CNC paths that you can see up here on screen. So we have 2 tool paths we're going to be optimizing here today. There's an adaptive milling path and a planar mill path. The goal here is to show you the ability that the software has in order for us to optimize this into using tools that typical CAM solutions like NX here don't have the visibility to do so. So what's really good about the production module software is its ease of integration with NX. So one of the things that I'm able to do is right over here in the top right, we have this third wave Exchange NX button. What this does is it creates an auto import of the actual CAM solution with all of the tools, the stock, the geometry, right into our production module software. So I'm going to click that now. It's getting all of that CAM information that I've just selected loaded up. It's popping up that window right now. So now over here, the Exchange NX window, it's going to give me a couple of options that I can use to start my project a little bit more seamlessly. So right here is a working directory. So I've already set this up ahead of time. So this is just where the project itself is going to be saved. So we've already got our example part CAM loaded up. Down here is our operations that we're going to be optimizing. So these are the same two CNC paths that I selected over here, as you can see. In this case, we're not going to make any modifications to those selected operations, but Third Wave does allow you to use helix and axial rake angle adjustments and radial rake angle adjustments. So the next thing we're going to do is we're actually going to select the workpiece stock for the software to optimize itself. So right now we're going to click Select Workpiece Objects here. We're going to overwrite the existing project from the sample, and right now it's going to ask me to select the workpiece. So this is our finished solution. So what we're going to do is we're going to uncheck the in-process workpiece. We're going to go back over to our part navigator over here, and we're going to turn back on our stock. So right now you can see in the translucency, this is the starting metal condition we're going to be starting with for that CAM cycle. So this is what the part looks like before we actually go into the optimization side of things. So all I do is I click on my stock body, I keep the auto detect resolution on, I say OK, and because we've already selected our workpiece material here, we're going to be pretty easy just to go down to the production module run forces. So this is going to be a good opportunity for me to talk to you guys about, while it's loading in the background, what is production module doing. It opens up production module and starts loading in all of the actual information. So this includes my CAM toolpaths, the tools, and this is a huge, huge time saver for anybody on the engineering field. It takes that duplication of work of all the work you just put into your CAM side, and it brings it right in. And as you can see in real time as I'm talking, it's already brought in my stock model. It's bringing in and analyzing my toolpaths in real time. These are things that a CAM solution is going to take a significant amount more time. So what this is intentionally doing in the background right now is it's using the finite element analysis software background that they have called Advantage to actually make a 3D simulation of the CAM cycle that I have. So it's making a full simulation with forces, with temperatures of what our cut is going to be in the machine, all without going into the actual machine to do any testing. I'm going to give you a brief walkthrough of what we're seeing now that the analysis is actually complete. So for now, I'm actually just going to close this window out. We're going to save the current optimization settings. So what you see on screen right now is a 3D simulation of the actual CAM cycle that I had in NX. So this is now the imported two toolpaths that we were talking about earlier. And what it's done for us is it's gone through every single cutter revolution, and it's made sure that it shows us these tangential forces that the cutter tool is experiencing while it's going through the CAM solution. So one of the things I'm going to do while I speak to this is start playing some of the simulator that I was speaking of before in the NX side of things. So what this software does is it created a full 3D simulation of that cut that's going to be experiencing on the machine. So what you see it going through right now is actually going through little by little, removing that stock material as it's going through. And one of the key things I want to kind of put a focus on is as it goes through in real time, it's tracking those cutting forces. Now, cutting forces is something that is extremely valuable to our engineering team. It shows us the predictive way to determine if a tool is going to break, if I'm going to have bad surface finish, if I'm going to be pushing the part, or at worst, even ripping it out of the fixture. You know, we really don't want to have any damage to our product, our machines, and we want to really prioritize the safety of all of our operators here. So while it's going through the simulation, some of the things that I'd like to kind of show is some of the ways that it shows the variables that we're typically unable to show here. So over here on our charts, which is where most of the data is going to be visibly shown, is our y-axis is where most of our really interesting variables are stored. So we started with tangential force, but you can also check radial, axial, load per unit length, you know, different types of specific feedback values. So we here, because we work with some thinner geometry, we typically like to stick with our tangential force. And what that shows us is that's where we believe is mostly correlated to our tools breaking down. And knowing when tool breaks down and getting ahead of that is one of the key points to keeping a stable production process. So one of the things that I see right away that I really don't think is something that would be a good process to run are these force spikes you can see here at the end. So these force spikes, as you can see, are considerably larger than any other cutting force seen throughout the program. You can see we're averaging around 150 pounds, and up here at our worst, we're right about 375, and that is really just too much for that tool to handle, we believe. So one of the things that I would say is a valuable spot for any cam engineer is knowing where the tool might be engaging its worst cutting parameter. And so in theory, I would assume from my engineering experience that these radii corners that we're going to try to finish here are where we're going to see that highest force, because that's where our tools fully engage with the product. And what that typically does is that puts a shock load on that tool. And because carbide is so brittle, you really never want to be shocking that tool, or otherwise it can shatter. So what I'm going to do is kind of highlight what the software's ability to do. As I click through this graph, it'll actually go through different spots on the stock itself and show me right where I expect to have those worst points. And so what I'm going to do is I'm going to click those couple of highest spots that we see here, and just as we suspected, they're right in those corners where that tool is fully buried. So what I like about this is a way to show your engineers who might be they listen to the machine by the feel of the machine, and it gives them data feedback that they can present to management that actually backs that experience claim. So what I like to see here is I need, from my cam solution, to bring that force down. Otherwise, I'm probably going to be breaking that tool. I'm going to be wrestling with it way too much. So what I'm going to do over here is I'm actually going to run over to the optimization spot of production module, which is the heart blood of how this truly works. So when I go through here, I selected my path, I go through my optimization, and what I need to do is I essentially need to make sure that this can go through its typical optimization. So it's going to go through the suggested parameters that I would typically like at first, just to get an idea of what it needs to be doing. And from there, I should be able to actually apply the paths over the actual existing cam solution. And so what this does is it allows us to compare before and after the optimization. So it shows us our original cam solution into the actual optimized solution. It takes a relatively short amount of time. I'll say as you get to more complex operations, it's going to take a little bit more time. But as you can see on screen, it's taking the amount of time that I would say is very reasonable to replace for changing out a physical machine test. So that's the number one thing that this software really does for us here at Neep, is it takes our most valuable resource, which is time on the machines, and it allows us to get these engineering tests and development done without ever actually going onto the machine itself. That is one of the key points that production module is really pushing for, is the ability to compress development without taking up your most valuable resource. And with this, it allows you to actually take a tool of development that you would typically put into the hands of your most experienced engineers and put the theory into hands of younger, newer engineers so they can understand the risks and the issues that are typically going to come from a development process. Now, one of the things that I think is extremely important to talk about here is the variables that no cam solution can provide right now is those cutting forces and tool temperature and chip load. It's able to show me values that I, as an engineer, would keep extremely, extremely valuable to keeping a stable process, and it gives me full visibility to them at every revolution of the tool. Typically, we're stuck with using theory, with forums, with background simulations from older software that's typically not nearly as accurate. And one of the things that what we're typically going to be working with is what we always want in a manufacturing process is to reduce my cycle time while still having the optimal tool life and the optimal machine health. So what that means is I want to push the machine as fast as it can handle, but I don't ever want to go beyond that speed limit, so to say. And one of the major ways that we watch for that is through force and temperature. So right now what you see on screen is the before and after of the optimization parameters I just ran. So these were just the base suggested parameters from Third Wave, just from looking at our cam solution coming in the door. So notice I didn't even select any other option. And with that alone, I'm able to show that those forces are now brought down and up to a more average level. You see that line gets a little bit more solid in the green. And the biggest thing to note is no more of those giant force spikes. So my highest force on this now is sitting at the optimized value of about 87 pounds. Now, typically, when you lower forces, most engineers would think I'm going slower, I'm taking lighter cuts, so I'm not going to be getting through my cycle nearly as fast. But the magic of what third wave is doing here is it's bringing up the lower cutting forces that are able to meet that cutting force optimization. And ultimately, as you can see here in the green, my cycle time stops right here. And to me, what that actually is saying, it ends at 624 seconds, whereas before it was here at 704. So I've saved roughly about 80 seconds alone just by using the options that Third Wave has within this production module software to give access to the variables that typical CAM solutions can't afford to parse up and split up. So what I want to talk about is how production module is actually going through and doing this. So what it does is over on the right here, you can actually see my toolpath view. So this is my line by line CNC program, and it's lined up exactly with where the simulation is. So if I go back to a different point in the simulation, it will jump that line to where it is. It's telling the machine to go to a certain coordinate at a certain speed. What it does is it takes those original paths that the CAM solution would link all together in one singular path. So it took these two separate toolpaths and converted them into thousands of individual toolpaths. What that does is in this small area where it saw the force that it saw, it's going to put a suggested feed rate for that exact spot on that CNC path. And that's something that the CAM solutions can't do unless you go through weeks of manual labor of parsing up these lines that I can promise you in 10 years I've never seen a single engineer do. Now, I took that weeks long activity and compressed it down to something I can present to you in under 10 minutes. So for me, that's something that shows its immense value, where I'm able to get the knowledge and trust of going into the machine with a more robust process right from the start. Under our operator conditions, we like to look at some of our feed rates from before. We like to look at also, so you can see here at the beginning and end where it wasn't doing its cutting moves, it harmonized that feed rate and brought it up to the maximum that we had set from the optimization. And where it wasn't making any cutting moves towards the end, which is where it goes home, it goes to that maximum speed the machine can do. So it's even looking at non-cutting moves to make sure that every single move that you do has its peak efficiency for movement. One of the other types of cutting conditions that we truly like to look at is also temperature. So one of the things that we want to replicate here is what we like to call the hot knife through butter effect. So the goal in any CNC cutting operation is you want the tool to be as hot as it can handle without losing strength. So with carbide, that's a pretty high number. That's actually roughly around 600 degrees Celsius. And so what I'm seeing here is that my peak tool temperature, now in Fahrenheit, it's a little bit high, but I'll say that that's well enough for the carbide. So as you can see here, the optimizer, even though we were pushing for higher feed rate and lower forces, it didn't feel that we needed to drop the temperature at all because it's still in that hot knife through butter Goldilocks range. And what that means is the carbide is as strong as it ever is at room temperature, but the actual piece that we're cutting gets so hot that it actually softens. And so the tool as it goes through is not fighting that really hard metal anymore, but it's really grazing through that just like butter. So one of the other things that we really like to do within this is show some of the other view options that you have. So number one thing that I'll say that engineers typically struggle with is expressing to upper management the reason for a need for improvement, especially when something may be running okay, but not as full optimization. So there's built-in process summary tabs that they have built in for quick demonstration. As we showed before, you have all of these various graphs that can show before and after. They can show positive benefit, all without even going onto a machine, which for any management is going to be a desirable condition. So one of the things that we truly do like to focus on, as we said before, was that tangential force, because one of the major ways that any shop is going to run its cost is going to be through tool life and through tool wear. And what you can see here, and I think it'll resonate with anybody even without as much of a technical background, that if I can get a part done at a faster rate but with lower overall forces, that is going to be a positive condition every single time. It's almost a guarantee that this is going to be a better run program than anything we could have put forward from a typical CAM solution. So I think what I want to highlight for a second is what this conversion from before to after would have looked like if we were to try to do this through a traditional approach. So what this would have required is we would have run the part on the machine. We may have actually broke the tool in the spot where these force spikes were, thus leaving us with a unknown how it might have finished. So what that would mean is the engineers would have to look into the tool. They'd have to be looking at the fixture for damage, checking the program, making different solutions available. And their only path for testing that forward with no certainty in sight is going back onto the machine and trying to recreate the run without the same failure mode. Now, that is typically right now based on theory, experience, collaboration. But what I've just shown is that a single engineer with the right variables and the right tool available is able to do this same interaction on their own without actually increasing any of the machine time that they're taking for development. And I think that's one of the things, especially me as a manager who doesn't get as much time to really get into the product as much as I'd like anymore. I really like showing that even a guy with my background and my experience is able to jump right into the project and show that there's opportunities for us to limit, reduce, and really get that overall shop capacity to its highest level. So one other thing that I'd really like to just show and highlight is some of the view options that Third Wave is able to kind of provide with the production module software. One thing that's really good to show off is actually the change in feed rate as we go through. And what you'll see is there's just a little color gradient of where it's showing you it's going fast and slow. So this is a great valuable educational tool for younger engineers so they understand not only why did the force need to be brought down and where did it get to, but what typical geometries are causing the cutting conditions that really is something that we might be able to even strategize around if we knew about this ahead of time. So say, for example, I didn't have my software. If I had this crazy force spike from before down at the end of this process where it was buried into these corners, I might have to be going to the engineer and telling them to find a different tool, a different cutter holder itself. And what I'm able to do here with the software is I'm able to show them that there is a much simpler path out without even needing to go into tool. However, if they wanted to do so, instead of going into the machine and trying to do a test with a better idea, they're able to go back into their CAM solution, program up an idea that they have, and rerun it through the analysis software. And what that allows us to do is have many potential iterations of experiments without even actually cutting the chips. And because of production modules built-in material modeling, that Third Wave does extensive testing to ensure that the cutting parameters match what's going on in reality with that material, we have extremely high confidence going into this machine that we're going to be more likely to have a first piece conformance right off the bat, which is the ultimate goal of any development process. If I could have it today, I would have the part tomorrow with a one click of a button, and with production module, we're getting closer and closer to that solution every day. One of the other options that it has is if you would like to, just because these charts are so valuable and you can keep this data, you're actually able to export all of your charts into an Excel format, which allows you to keep that in a database of history of your continuous improvement. So that way you can show your management, hey, from every run through this optimization software where you learn a little bit more, you can show that you can get, on average here at NEAP, we get around 20-25% total reduction on cycle time. And we're still even looking into how much more we can get on tool life. But as you can see with the reduction of forces here, we're able to get to the grand total of the ideal development situation where we walk into the machine knowing right away that we expect to have a conforming part off the machine. Other things that can be done that are really helpful educational tools is as you're running through the simulator at any time, you can actually do a refresh to stock, which brings back in that stock model from NX and allows you to show some of these younger engineers or these newer engineers who are new to the tool exactly what they're seeing at the rate. So this is running our new optimized code now. And so you can see it's following that green bar under here. And what it's really showing is where at any moment, if I wanted to stop and have an engineer understand why they're seeing what they're seeing, I can pause the animation and I can actually go one revolution of the tool at a time. So think frame by frame. So as I go through, you can see that black bar on the right side jumping around based off of where the actual tool is. So I'm going one line at a time, as you can see on that right toolpath view over here. Every time I click this arrow, it's going to jump down to that next line. And that's why you can see those forces jumping as it goes through. So when I play through, say for example, I wanted to find what it looked like at the highest peak, I would go until I see that bar at the highest, and I would even rotate my view while it's doing the simulation, and I can zoom in on the actual spot where it's having the problem. And right away, again, as we see, that tool is essentially buried in that workpiece. And if the tool is buried in the workpiece, all of those cutters are engaged at once. And with that happening, that's an ideal solution that we don't want to have at all times. But since we ran our optimizer and we set that feed rate, we're still pretty happy with the overall result. But at least it's good that I can show even people with less technical background exactly where we've solved the problem or lack thereof if we haven't run the solution yet. So one other thing that it's also able to do is it is able to do a quick little sequence view of the part itself. So one example there is we use through load per unit length through that sequence view. As you see here, it actually brought up the load per unit length. Now that's a valuable variable for engineers to use. And what it did there is it still used that same optimization value it had right in the beginning. So if I were to click back into the window, you'll be able to see the forces that we're talking about and where those lines are. So right here, you can see this 86 pounds for that tangential force. And you can see right here where that black bar is it tried to keep as many of those forces underneath that black bar or bring those lower ones, as you can see where there's no green in this middle pocket here, up to that same value. And you can see I have no value in here that's underneath that when we go over here. On the load per unit length, this is our limiter. So this tells me that I'm not able to push my tool too much more on this variable as well. And you can see on the previous result here, on the red, we actually were lower. But what we did is by using that 86 pound force, we allowed it to bring that number up. And because of that, you can see here on both graphs, that cycle time reduction is clear. And again, this is on the suggested values. I could talk all day about how many additional options that third wave gives you to optimize your program with. For example, one of the ones that we like to use here at an airfoil shop, because we deal with extremely thin geometry, is tooltip deflection. I think everyone can understand if my tool deflects away from my part or vice versa, I'm not really going to have the dimension that I want at the end of the day. And so this is telling me that it's good. If I wanted to, on my thinner parts, I could limit my tooltip deflection by almost to 1/1000th of an inch, and that would allow the FEA software in the background Advantage do its magic to make sure that as my cut at every revolution is going, that tool is not going to try to back away or that material is not going to push away from that part and compromise the integrity of the actual cutting surface. That is really the gist of how we use production module here at Neep. And our plan for the future here is to ingrain this as the base of every development project that comes through here. So that way, before we're interrupting in anything in the production environment, we're making sure that we have compressed the most amount of time out of that development cycle as possible, which makes it a win-win across the board.
We found a way to serve the Army to the levels of pre-COVID with tweaking how we do things on the manufacturing floor. And I'll go back to CCAD because I think CCAD really is that facilitator that we're going to help you guys, we're going to do this with you, and we're going to get to the other side together, and this will actually work. They have the ability to bring these newer technologies, really test them out, and then think of the applications it can have in the manufacturing world that's around them. Neep and the employees that work here take a lot of pride in supporting the AGT 1500 or Abrams tank and the Army. Great pride when we know that we made the deliveries, that we were on time, and that we're kind of contributing to the fight for freedom all around the world.